Let's solve some problems involving horizontally launched projectiles. Now, whenever we deal with any projectile, whether it's launched horizontally or at an angle, we know that the x motion has constant velocity, but the y motion does not. The y motion has acceleration, which is negative 9.81. If there's constant velocity on the x-axis, then the equation would be just this one. This is the equation of constant velocity. On the y-axis, though, when we accelerate at a constant rate, we use these equations. The first thing I want to point out is that even though this says vi, it's really just the initial velocity on the y-axis. So you might prefer to show this as viy and vfy to remind yourself that you're only talking about the y-axis component. Okay. Number 30, the first question says, a marble rolls horizontally off the table with an initial velocity of 5 meters per second. So we could label the picture so that this is 5 meters per second. As soon as you see this statement, you can ask, well, how much of that 5 meters per second is on the x-axis? The answer is all of it. How much of that 5 meters per second is on the y-axis? None of it. So VIY is 0. And of course, anything multiplied by 0 is 0. Let's see. This is 0, this is 0, and this is 0. It enters free fall, which means the acceleration is negative 9.81, of course, meters per second squared. And then before we look further into number 30, let's look at number 31, or 32. Let's try 32. Okay, 32 says, a dart is thrown horizontally at 5.52 meters per second. Well, in that case, we would ask the same question. How much of that velocity is on the x-axis? All of it. So the x velocity is 5.52 the entire time it's in the air. This velocity is constant. The x velocity doesn't change because gravity doesn't pull left or right. How much of that 5.52 meters per second is on the y-axis? None of it. So once more, VIY is still 0. In fact, for any problem where you launch the projectile horizontally, you will always have VIY equal to 0 if launched horizontally. So that's kind of a nice, simple fact. Well, let's look now at the middle problem. The middle problem says, a child throws a baseball horizontally. Okay, take note. She throws it out of her window, which is 2.6 meters off the ground. The baseball lands on the ground, and it has traveled 15 meters forward from the window. Calculate the initial velocity with which the baseball was thrown, assume free fall. Well, if we're looking for the initial velocity, of course, that is equal to Vx. If we can find Vx, we will know the initial velocity because Vx is equal to the initial velocity. This whole thing is on the x-axis. None of it is on the y-axis. So we now have two facts that are always true for horizontally launched projectiles. It's the two things in green. Okay, let's actually look at the solution for these, and this will take just a couple of minutes. Number 1 gives us a marble launched horizontally at 5 meters per second. Immediately we know Vx, it's 5, and we know VIY is 0. We read on, it enters free fall. Yes, negative 9.81 meters per second squared. That's the acceleration. When the marble lands on the ground, so if it lands on the ground, then the final height, the final y position is 0. Okay, it lands on the ground. It has traveled 11 meters forward. This is the distance traveled in the forward direction, that means this is delta x is positive 11 because forward is positive. Determine the height of the table. Well, hang on. It starts up here. It ends down here. If we find delta y, if delta y tells us how far down it traveled, the height of the table is just how high up it began. So we need to find delta y. Okay, how do we find delta y? Well, we're going to need one of these equations. And we know acceleration, but we don't know time. We don't know VF. We don't know VF or time here. So we can't really, again, we don't know VF or time, but there's one equation, this one. All we would need to do to use this equation is find time. How can we find time? Look back to the x-axis. Vx we know, that's 5. Delta x we know, that's 11. So we can solve for the one unknown time, and then once we get it, we plug it in here and find delta y. If delta y is like negative 5 meters, or I don't know, who knows, then the initial position, the height of the table, is positive 5 meters. And you can use y final equals 0 to prove that that's true. Number 31 is a very, very similar problem. This time, we are trying to calculate the initial velocity. But of course, that means we're trying to find Vx. In this case, they've given us the delta x, but until we know time, we can't get Vx. So that's what we do. We find t first, just like the last problem. How do we find time? Look at the y-axis motion. So if we look at the y-axis, what do we know? They've given us the initial height, y initial, and they said it lands on the ground, so we know y final is 0. If you do final minus initial, we know delta y. We also know the acceleration. So from that first equation, we could calculate time, plug it in right here, along with delta x, and find Vx, the x-axis velocity. But of course, because the projectile was launched horizontally, the initial velocity is just the x-axis velocity. All of the initial is on the x-axis, so if you know this, you know that. 32 is very similar as well. In 32, we are given the initial velocity of 5.52. We know how high it is off the ground, and we know it hits the ground. So using those things, you can find delta y. We know it's in free fall, so the acceleration is known. And what else do we have here? Well, we are trying to find the horizontal displacement by the time it hits the ground. You may be inclined to say, you might be tempted to say Vfy is 0 if it hits the ground. But this would not be correct, because if you actually let it strike the ground and slow down and bump into the ground, as soon as it actually touches the ground, it's no longer in free fall, and none of these equations apply at that point. So we cannot say that Vfy is 0. Instead, Vfy would refer to that final speed in the y-axis direction right before it actually hits and slows down. Okay. So what can we do? What can we use to solve? Well, if we're looking for delta x, clearly we need to know the time, because this is the only equation with delta x. How do we find the time? Find t first. How do we find time? The same way we've been doing all along. Look over at the x-axis. The y-axis. Look at the other one. Is there an equation that lets you solve for time? Well, it's going to be the first one once more, because just like before, we have delta y, we have a, this is all 0, because it's launched horizontally. So we can solve for time. Then we take that time, plug it in along with the 5.52, and we calculate delta x. And that's the kind of process we'll be using to solve these problems.